Hello, my name is Kurt Beschorner. I'm going to talk about the tread friction finite element model that our group has developed. I should make sure to acknowledge Pavan Mogharam, who was really central to the development of this model. So I'm going to talk about the mechanics behind it and a little bit about how it works and why it's useful. So a floor surface may look flat, but if we zoom in on that floor surface, we find that that surface consists of many peaks, like a mountain peak, and many valleys in between that. And so if we think of one of those peaks as being like a needle, so that we can think of this triangle here as a single peak of a floor surface, and that this peak is sliding relative to a shoe surface. And so the interesting thing about shoe treads is that rubber and rubber-like materials, when you push them in and then let them go, there's some amount of energy loss. So it takes more force to push them in than what is returned when you let them go. And that is an effect that we know as hysteresis. And so this is shown on the graph on the right, and you see this, this light blue line that shows the force that's required to push in the tread. And then this gold line shows the force that's returned to it as the shoe relaxes. And so we're going to watch what happens to a single piece of shoe material as this floor mountain, as this floor peak, or we can think of it as a needle, as it as it drags by. So on the front end of this mountain, we're going to see it follow this light blue curve, and on the back end, it's going to follow the gold curve. So I'm going to show you that again. So remember, it takes lots of force to push this piece of shoe material up, and then you only get a little bit of that force back on the other side of the what we call the asperity or the mountain peak. And so in reality, floors consist of many of these peaks and many of these valleys, and at each one of them, we see that just as we saw before, it takes a greater amount of effort or a greater amount of pressure to push in that piece of floor material than what is returned when the material relaxes. And so that leads to an imbalance in the forces on the two sides of this mountain peak or of this asperity, which leads to a net force in the direction opposite of sliding. And so that's a type of friction that we call hysteresis friction. And so it's a mechanical phenomenon. So it's something that can be modeled in mechanics software. And finite element analysis is a really great way to simulate material mechanics. And so we developed what we call a multiscale model, which means that the model operates at more than one scale. And so one of those scales is at a micrometer scale, which is the zoomed in scale. So at the micrometer scale, most floor surfaces, you will see noticeable peaks and noticeable valleys. And so our model simulates what happens when you have a rough shoe surface with peaks and valleys sliding against a rough floor surface also with peaks and valleys. And so what we note from our microscopic model is that the coefficient of friction, or the amount of friction force for a given level of normal force, that this decreases as we increase the contact pressure. So as we have higher contact pressures or more concentrated weight, we see that the coefficient of friction decreases. So we can take that information from our microscopic model, we can take these curves, and we can combine them with a whole shoe model. And so a whole shoe model will give us the contact pressures at each individual point along the shoe tread. And so we can map those curves onto these contact pressures and figure out what the coefficient of friction is at each individual point. We can bring all that information together and get an overall estimate for the coefficient of friction for that shoe. And so we've done that with a number of shoes and different floor surfaces, and we find that we get very good agreement between coefficient of friction that's predicted by the model, which is on the x-axis here, and experimental coefficient of friction data, especially oily coefficient of friction data, which is on the y-axis here. And so why is that useful? Well, one reason is that predicting shoe friction performance before you go to prototype can save a lot of money. So that's one benefit. A second benefit is that it will tell us the regions of the shoe that are causing performance to be lost. And so we can think of pressures as being represented by a heat map where the red regions are our high pressures and the green regions are our low pressures. And so we can see in this region of the shoe, we have low contact pressures, which are giving us relatively high coefficient of friction values. We see these regions here, which are giving us sort of moderate contact pressures in the yellow region, and that's giving us a little bit lower of coefficient of friction values. And then we have these regions that have high contact pressures, and those are giving us the lowest coefficient of friction values. So this model will tell us that if you want to improve the performance of the shoe, then you need some design change to reduce the contact pressures, especially in this region. So that's how the model works. That's why it's beneficial. If you would like to continue this conversation, please find me on LinkedIn under my name, Kurt Beschorner. You can also reach me on Twitter or email me. If you have any questions, I would be more than happy to talk about it in further detail. Thank you very much, and that's all I have.